viewers, welcome to Gurukul Live Lecture. Myself Dr. Preeti Jagwani from Department of Computer Science, Aryabhat College, University of Delhi. Today we will be discussing dynamic implementation of two very important data structures, stacks and queues. So the agenda for today will be, firstly we will understand the implications and the need of dynamic implementation. Then we will go through stacks and its operations through dynamic implementation, insight into its various important applications, and then finally we will be covering dynamic implementation of queues. So firstly, coming to what is dynamic implementation. In the previous lectures we have seen the static implementations of stacks and queues both. So stacks and queues both can be implemented whether using static strategy or dynamic strategy, both. So dynamic implementation is actually the implementation at runtime. That means at compile time you need not to assign the size of the data structure. Size of the data structure is not fixed here, it can be modified during the operations performed on it. That means it can grow in the size or it can shrink in the size. So that way it offers more flexibility to the user or to the application. So to understand it in more detail, let us consider the implementation of a stack using an array. So array, let's say we have of size 10 and we are using a stack of let's say 5 elements. So 5 elements of the array will be wasted, and if we want to insert 11th element or elements more than 10, we can't insert it unless we dynamically reallocate the memory. So in order to avoid all these issues, we can go with dynamic implementation. In dynamic implementation, each and every element will be given memory at the runtime as and when required. There is no fixed size at the compile time. Now, how stacks will be implemented using this dynamic strategy. So this will be an operation, or this will be the idea which is based on linked list. In linked list, here when we implement a stack through the linked list, that is known as dynamic implementation of stack. In it we can allocate the memory dynamically. Each and every node will be having two elements. One is data and another one is the next, which is the pointer pointing towards the next node, and the last node which is known as top. That's the normal terminology which we follow in stack. So nodes are maintained non-continuously in the memory. There is no continuous allocation of the nodes in the memory, and each node contains a pointer to its immediate successor node in the stack, and the topmost node in the stack always contain null in its address fields. So here we can see on the screen that we can implement this is the way in which we can implement a stack dynamically. So node and data, node data is the one data element, and then next pointer is pointing towards the node upper in the direction. Similarly for the node 2, it is also pointing towards the node 3, and the node 4, which is the topmost node, it is not pointing towards any other node there. That's why its pointer field is empty, or it is in a way it is containing null. So here stack is said to be overflown if the space left in the memory heap is not enough to create a node, which is normally nowadays not a situation. So here using the dynamic implementation, one more advantage is this: we are out of these overflow problems kind of thing. Yeah, but underflow is going to be there when there is no element present in it. So stack, if it is not having any element present in it, that is known as underflow. And overflow condition is when heap is not having enough memory to assign for the next element, which is generally not the case. So, what are the common operations on these stacks is push, pop and traverse. All these operations we have also seen using static implementations. Pushing an element to a stack in linked list is actually different from the array implementation. That means the dynamic implementation, pushing an element using the dynamic strategy, is altogether very different from pushing an element in the static strategy. So, here we will create a node first and then allocate memory to it. So, creation of node is basically allocation of memory. Allocation of memory can happen depending upon what language or what application you are using. So, you can take a node class if you are using an object oriented programming language, or this node can be implemented as a simple structure for which memory can be allocated using malloc or calloc if you are using a non object oriented programming facilitated language. So, if the list is empty, now in order to create the stack, or in order to start with, let us say list is already empty, then the item which we will be pushing will be the start node of the list. This includes assigning values to the data part of the node and assigning null to the address part of the node. That means that will be the first element which will be inserted. Or another case could be, you can already have an stack created and you want to push an added element, or you want to push another element onto it. So, if there are some nodes in the list already, then we have to add the new element. Now, where? In the beginning of the list, so that we should not violate the property of the stack. That means stack is a LIFO structure, that is last in first out structure. So, in case of that LIFO structure, the element will be added only on the top of the list. So, for this purpose, if your stack is having already having some elements, assign the address of the starting elements to the address field of the new node and make the node the starting node of the list. This is one case. Another case could be, you can have one node on top of the already existing nodes. So, here is the figure of these dynamically created stacks. So, here we can refer the topmost node by using head pointer, but the actual terminology should be top in case of stacks. So, if we want to insert one node as it is shown in the second figure at on the screen, we can create a memory for the node, and then our head or top should point to that particular node, and in the address field of that node we will be storing the address of the previous top pointer. This will be the scenario. In order to implement, we can check if top or head equals to null, that means it is having no values presently. So, whatever value will be of that pointer, PTR is a pointer variable which is pointing towards the newly created node. So, that data or the value val element will be equals to the value which is being passed by the user as the new data element, and then its next pointer or its pointer will be pointing towards null. And obviously, as this is the first element, we will be assigning the value of pointer to the head. That means now the variable PTR and the variable head or the variable top both are pointing towards that only node present whose value is equals to the val element and whose next pointer is the null element. So, now in a way we are having one element in the stack. Another case could be where head is not equals to null. So, if head or top is not equals to null, that means your stack is already having some nodes populated into it. So, we will be assigning we will be assigning memory dynamically to one node. Now, this memory you can assign using malloc, calloc, as I have already discussed, whatever the strategy is. Then the its address of that particular memory or address of that particular node is being captured in the variable PTR. So, value of PTR will be the val given by the value of the element given by the user, and the next pointer will be pointing towards head. Now, as you can see here, if I am going to create one node which is node 0, so node 0 is having its value as the val, and the address is pointing towards the previous top which is given by the head. So, I am just establishing a link between the node 0 and node 1 in the second line of this else statement, where PTR next is equals to head. That means, whatever value a head is having will be given to PTR next, and head is pointing towards the node 1, and so as next pointer of the PTR, which is node 0, will be pointing towards node 1. So, now this node 1, which was previous top, is having two links. One is coming from the top pointer or the head pointer, and another one that is coming from the node 0. Now, what we need to do next? Next we need to do that in order to make the top element as the last input, we need to set the pointer of head to the PTR. So, value of PTR will be given to the head, which will be given by head is equals to PTR, and the link between the head pointer and the node 0 will be established here. So, in a way, now head is pointing towards the new node, and the new node is pointing towards node 1, node 1 is pointing towards node 2, node 2 is pointing towards node 3, and so on and so forth. So, now that node 0 or the newly node entered is available on top of the stack. So, we need to be very careful that we should not violate the properties, the basic characteristics of the stack. Now, coming to deleting a node from the stack, which is actually technically known as pop operation. So, before going with pop operation, we need to check for the underflow condition. As I have already told you, overflow in dynamic implementation is not actually a major problem, because we have huge amount of memory generally, but the underflow condition occurs when we try to pop out from an already empty stack. So, how are we going to check that stack is already empty? So, the stack will be empty if the head pointer of the stack or the list points to the null. So, if head equals to null, or if head equals to null, this condition is true. That means your stack is not having any element, and this is the condition of underflow. Next, what we need to do, in stack the elements are popped only from the one end. We all are aware with this. So, therefore, the value stored in the head pointer must be deleted and the node must be freed. The next node of the head node will now becomes the newer head or the new head. So, this can be done by, if head is equals to null, we can say underflow and then exit. We must exit from the program or from the subroutine. Else we will take the value of the or the, you can say, data item into the value into a variable item, and then we adjusted head equals to PTR, because we don't want to delete the pointer head, we want to delete a temporary pointer. So, that is why we have taken the value of head into PTR. That means, now PTR is also pointing towards the top element, and the element which is contained in the head is contained in the item variable. Now, head will be pointing towards the next element, which is accomplished by head is equals to head next. Now the pointer is pointing towards the first element, head is pointing towards its next element, which is the second element. So now we can always, without any hassle, we can say free pointer or release the memory which is occupied by the variable pointed by the PTR variable, and then we can say item popped, and if we want to print the value of popped item, we can print that value which is contained in the item variable. So in a nutshell, we have taken that value in a variable, we have assigned a temporary pointer pointing towards the head node, shifted the head node, and then freed the already assigned PTR value, which is the first value. So that can be done very trivially. Then coming to traversal. Traversal is actually displaying the nodes of a stack which is available in the form of a linked list. Now that linked list is organized in the form of an stack, and we need to traverse that stack. So what are we going to do? We just need to keep on printing the values which are pointed by the head pointer, and we need to shift the pointer. But here the problem is we should not and we must not shift the head pointer, because that is one reference pointer or that is one pointer which will be required for further operations also. So for this, what are we going to do? We copy the head pointer into a temporary pointer, and then we move that temporary pointer through all the nodes of the list and print the value of the data field attached to every node. Now programmatically or pseudocode wise, this can be done in a very simple manner, but before traversal we also need to check that whether your stack is already empty. That means if a stack is already empty, we cannot traverse it, that is very obvious. So value of head is assigned in a temporary variable PTR, and if PTR equals to null, we will be printing that stack is empty, obviously it can't be traversed. Else if it is not the case, then in order to print the stack elements, we will keep on printing the value of PTR well or PTR data while PTR not equals to null, and also we keep on shifting the value of PTR to PTR next. So coding wise we can say while PTR not equals to null, print PTR well, and then PTR is equals to PTR next. That means while your PTR is not coming to null, you print the value of the data element pointed by the PTR and then shift the PTR to the next element in the list. So this in this way traversal can be done, but we need to be very careful that we need to check that whether your stack is initially empty or not, or we can print some elements over from here. Now coming to applications of stack. So if we can look into applications of stack, there are various applications of stack in computer world as well as in real world also. So in order to summarize a few of them, or in order to list a few of them, these are conversion of decimal into binary, conversion of expression from one form to another. So one form to another is, let me summarize it. Expression can be written in three forms: prefix, infix and postfix. So in prefix situation, your operator comes before the operands. In infix, your operator comes in between the operands, and in postfix expression, your operator is always followed by the operands on which it is to be operated. So in conversion of expression from one form to another, stack is having its own utility. In conversion of decimal number into binary number, it is having its own usage. Then evaluation of expression, that is if we want to evaluate in postfix expression or in prefix expression or in infix expression, whether it is properly parenthesized or not, both the cases can be handled very efficiently by stacks. And recursion, which is well known application of stack inside the computer world, or in the computer world is one application, is another application. Now the list is, this list which I am telling you is not exclusive. It is having, you know, in scanning the parsers and other many areas, in backtracking, in maze problems also, stack is having its own wide variety of usage. Now let me elaborate some applications of stack. First I will be taking conversion of a decimal number into binary number. So what is the basic logic of conversion of decimal into binary? We will keep on reading a number, that means we will be while number is greater than 0, we will take the remainder by dividing the number we will be having in the hand, either 0 or 1. We need to print that remainder and divide the number by 0 in order to make it half, and then we need to end the iteration. This is what a basic logic for decimal to binary conversion is. Reminders we keep on taking, and then the next number will be the number divided by the original number divided by the 2. Now what is the problem with this logic? Problem with this logic is, let us say we take binary of 23. So as per this particular logic, if we keep on printing the remainder as and when it comes up, binary of 23 will be 11101, but this is not correct. Binary of 23 is 10111. That means it is just inverse of it. So by this logic, binary of 23 will be printed as 11101 instead of 10111. So what is the solution here? For the solution, the stack comes into the picture. So idea is to exploit last and first property of the stack, because we need the remainders or the numbers in the reverse order. So be careful, wherever you need a reverse printing or a reverse traversal or something which is not, it is just opposite of the way it is coming, stack can be a very helpful data structure. We need to push the binary digit from the stack instead of printing it directly. Don't print the remainder directly, just push that remainder onto the stack, and after that entire number has been converted into the binary form that it is kept on the stack, pop one digit at a time from the stack and print it. So we have inserted let us say 11101, and when we will be popping out, this will come as 10111. So we will be having our own correct version of the binary number. So in this way, this decimal can be converted into its proper binary form by exploiting or by using the last and first LIFO property of stack. In order to do this, we need to create a stack first. We enter a decimal number. While decimal is greater than 0, we take the remainder by 2. This is stored in a variable which is digit. Now push digit into the stack. In the earlier version, we were printing this. Now we are not going to print the digit into the stack. Also be very careful that we need to keep a check on the overflow condition here if you are implementing the stack statically. If you are implementing it dynamically, then there is no need to check the overflow condition in the normal scenarios. Then we divide the number by 2, and then we keep on doing this while till our number is greater than 0. In the second iteration, we will say, while my stack is not empty, I will keep on popping the digits from the stack and print the digit. As the digits are available on the stack and we are popping them one by one, this LIFO property ensures that our number comes in the proper binary format. Coming to the next application of stack, which is conversion of infix to postfix form. So infix, as I have already told you, is going to give the operator in between of the operands, which is, let's say, a plus b asterisk c plus d. So considering the first operator, which is plus, the operand on which it is going to be applied is a plus b if we don't consider the other part, or asterisk operator is going to apply on b and c. So asterisk operator is in the middle of b plus c. So normal expression format which we use in mathematics is infix expression. And coming to postfix expression, the postfix expression for this infix expression a plus b asterisk c plus d will be a b c asterisk plus d plus. That means putting up the operands after the putting up the operator after the operands. So first of all, let me establish the need why this postfix expression format is required. Let's say inside the computer, a compiler first scans the expression to evaluate that particular expression. So according to the Bodemus rules, in the expression a plus b asterisk c plus d, it will evaluate b asterisk c, which is b multiplied by c according to the Bodemus rule. This will be the correct idea. Then again it scan the expression to add a to it, then it will, the resultant will be a plus b asterisk c, and finally its result or its intermediate result will be added to d after another scan. So in order to evaluate this small expression, the compiler needs to do the scanning thrice. So this repeated scanning is inefficient. But if it goes by a plus a b c asterisk plus d plus, which is the postfix expression or which is the postfix format of this particular expression. So in one scanning it will say a b asterisk c is the first thing, and then it will plus the, it will add the a, and then it will add the d. So in order to avoid this inefficient repeated scanning, postfix is the preferable format of expression. So in order to convert infix into postfix, we need to scan the infix expression from left to right, symbol by symbol. That means one character at a time. So now we need to do now we need to apply different strategies on whatever symbol we have taken, if whatever symbol we have scanned. So if the scanned character or the scanned symbol is an operand, we will be putting it onto the output string. This output string will serve as the postfix form. Else, other ideas or the other scanned characters could be opening braces, then closing braces, or it could be an operator. Now, in case of an operator, we need to see whatever is available already onto the stack. That means in order to scan the infix expression, in order to convert the infix expression into postfix expression, we need to take a temporary stack. Now we will keep on scanning the expression symbol by symbol. One, we are having our stack, and another we are having our output string, which will be the postfix string. Now scanned character, if it is an operand, we just put it onto the postfix string or the output string, we can say. Now if it is an operator, we need to see the contents of already available stack over there. If the stack is having an operator as its topmost symbol, we will be comparing the precedence of the topmost symbol of the stack and the precedence of the operator scanned. If the precedence of the scanned operator is greater than the topmost symbol, which is the operator in the stack, we can simply push it. Or if the stack is empty or stack is containing an single parenthesis, we will be pushing it. In case of the operator which is scanned is having a lower precedence as what is available on the stack, we cannot push it directly. In that case, that means a higher operator symbol cannot be pressed upon by a lower operator symbol. Then we need to pop all the operators from the stack which are greater than or equal to in the precedence than that of the scanned operator, and then after doing that, push the scanned operator to the stack. That means you cannot suppress a higher precedence or the equal precedence operator. You need to take or you need to pop all those operators and you need to submit them to the your output string. If you encounter parenthesis while popping, then stop there and push the scanned operator in the stack. Now coming to, now this was about operators and operands. So if it is just an operand, we need to output if it is an operator, we will be go by precedence. If required, we can pop all the operators of the higher precedence and send them to the output string, or we can push the scanned operator directly depending upon what is the precedence seen between these two. Now if the scanned character is an opening parenthesis, we push it to the stack, but if the scanned character is in closing parenthesis, we need to pop the stack and output it until an opening parenthesis is encountered, and then we discard both the parentheses. Discard both the parentheses means we need not to put these parentheses whether opening or closing in the output string, which is the postfix string, because postfix form is always free of parenthesis, and then we will keep on repeating this these steps until the expression, until the final expression or the whole expression is scanned, and we will be printing the output. Pop an output from the stack until it is not empty. Let us consider one example for this whole scenario, which is conversion of infix to postfix. Now we are having one expression which is a plus b multiplied by b, b multiplied by c in parenthesis. Now one by one we will be reading character or we will be scanning the symbols. We are having one stack and we are having one output string. So we will be reading the first character from left in the infix string, which is a. Stack initially is empty and we will be outputting, we will be sending it to the output string, because this is just a you can say operand. Then we have plus, which is an operator. Operator are to be stored on the stack. We will be storing it on the stack. Output string is still having a. Then the next symbol scanned is parenthesis. Parenthesis will also go on to the stack and the output string is status quo. Then we will be scanning b. B again will go to the output string and stack is status quo. Then asterisk. Asterisk, as it is an operator, we need to push it onto the stack. So now our stack is having plus opening parenthesis and the asterisk, and the output is having a and b, a, b, that's it. Coming to the next symbol which is scanned is c. This will be directly going to the output string. Now the output string is a, b, c, and the stack is having plus opening parenthesis and the asterisk. Now the next symbol which is encountered is closing parenthesis. Now please remember, in case of closing parenthesis, we keep on popping the asterisk unless we till we get the opening parenthesis. So we have popped it and we have got one symbol which is asterisk symbol, as you can see on the screen. So we have now that asterisk symbol is given to the output string, and now both the parentheses are discarded. What are we left with onto the stack is having one plus symbol, and as our infix expression is complete now, we will keep on popping the elements from the stack, and we will keep on submitting those elements onto the output string. So, the converted form of the infix expression A plus B multiplied by C in parenthesis will be A B C asterisk plus. Now, this form, postfix form, is always free of parenthesis. So, conversion of infix to postfix, or rather than any other form from one form to another for that matter, can be very efficiently done by using stacks. Coming to the next application of stack, that is evaluation of postfix expressions. We have one postfix expression and now we want to evaluate its value. For that, stack is again a useful data structure. We first of all we add the closing parenthesis to the postfix expression. This will be treated as the sentinel, which will flag the kind of, you can say, end of the postfix expression. And now we will start reading postfix expression from left to right until that particular closing parenthesis is encountered. So, closing parenthesis here is just a sentinel element, nothing much. So, if an operator is encountered, we push it onto the stack, and if an operator is encountered, we need to pop the two topmost elements from the stack, which is A and B, and then we evaluate B operator A. Whatever the result of B operator A will be there, we will be pushing that onto the stack, and then this will keep on continuing. Either we will be having operand or we will be having operator. So, if it is an operand, just we need to push it, and if it is operator, we need to pop the two elements, evaluate them by B operator A. Now, here this is very important, it should be B operator A, it should not be A operator B. That means, if the symbol is, let us say, B operator A is B divided by A and A divided by B, these are two different things. So, we have to be very, very careful here. We need to evaluate B operator A, not the A operator B, where A is the topmost element is taken from the stack, and B is the second element, or you can say next to the top element, and then we will be getting result and we will be popping it out. For this, let us consider one more example. So, if, the postfix expression here is 562 plus asterisk, then you have 12, 4, slash and then minus. So, first of all we need the input symbol, we have a stack and some immediate calculations, which are, you can say, immediate calculation, and finally this immediate calculation will also give us output. So, scanning the first symbol gives us 5, directly push it onto the stack, then it gives us 6, again push it onto the stack, coming to similar treatment. Now, the next symbol which is scanned is plus. Now, what we need to do? We need to operate this plus with the topmost two symbols, that is 6 and 8. So, 6 plus 2 will be 8, and then 8, this result, intermediate result, will again be pushed onto the stack. Then again the next symbol is asterisk, and then asterisk. Now, we have 5 and 8. So, 5 and 8 will be evaluated using asterisk, the intermediate result is 40, and then we push 40 onto the stack. Then the next symbol scanned is 12, 40 and 12, these both are now lying onto the stack. Then we have 4, then now the stack says 40, 12 and 4. Then we have divide sign, we need to pop two elements, and here it is come, this will be 12 divided by 4, not 4 divided by 12. So, 12 divided by 4, which is B operator A is going to give us 3. So 40, and this 3 will be again pushed onto the stack. So the stack is having now 40 and 3. Now again we have next the sign which is minus. Now with these two operators, with these two operands 40 and 3, we need to operate this minus sign, which is 40 minus 3, and that is 37. 37 again is pushed onto the stack, and as we have no more elements, 37 will be considered as the final value, final result. Last but not the least, a very important application of stack structure is recursion. So what actually a recursion is? It is a very common technique used in computers. It is expressing a given problem in terms of itself, a function calling itself, you can say. For example, we need to find the sum of elements of an array. We can easily say that sum of array will be equals to the first element plus sum of the remaining elements of the array. Here in case 1 plus the sum of the remaining elements of the array. So again we can say 2, 3, 4, 5, 6, 7, 8 is the remaining array. So this remaining array will be treated similarly, that is first element plus the sum of the remaining array. Remaining array 3, 4, 5, 6, 7, 8 will be treated on the similar basis, 3 plus the array, then 4 plus the array, 5 plus the remaining array, 6 plus the remaining array, and 7 plus the remaining array. So essentially what we have done, first element plus an array of the rest of the elements, second part itself is an array whose sum is again its first element plus sum of the remaining elements, and so on. So we have behind the scene what is happening? Behind the scene it is happening that we have modularized the problem in its own format. So here what is happening, when a function calls itself, a stack is required to store every function call. Every individual function call will be stored as an element of the stack. Consider a very common application of recursion is factorial. Now we have an module which is factorial. So we need to return if n equals to 0, we will be saying it is 1, and if n is not equals to 0, we will be returning n into factorial of n minus 1. So here the module factorial of n is calling factorial of n minus 1. So again that factorial of n minus 1 will apparently call factorial of n minus 2, then factorial of n minus 2 will apparently call factorial of n minus 3 until your n becomes 0. So when your n becomes 0, it is going to give me 1. So this terminating condition is known as the base case in recursion. So what happens actually here? So we have one global area where global elements are stored. Now let us say your n is 3. So this will be n, obviously it is not equals to 0, it is not equals to the base case. So it will go on calling n into factorial of n minus 1, which is 3 into factorial of 2. In the next step, this factorial of 2 will be calling 2 into factorial of 1. So essentially what is happening, factorial of 3 has called factorial of 2, factorial of 2 will be calling factorial of 1, and then factorial of 1 will be calling factorial of 0, and so on and so forth. So for every function call here, a stack is used, and every function call gets its placed on the stack, as you can see on the screen. So 3 into factorial of 2, in order to evaluate factorial of 2, this will call 2 into factorial of 1. In the next step, 2 into factorial of 1 will call 1 into factorial of 0. Now factorial of 0, where n equals to 0, gives 1. So now here is the place where your stack starts unwinding. You have 1 into 1, and that is returned, that intermediate result is being returned, that element is being popped. So, coming to the next part of this, coming to the another half of this image, we can say 1 into 1, we can see 1 into 1 is 1. Now, this 1 into factorial of 1, then 2 into factorial of 1. So, factorial of 1 is 1. In the next stack line, it is saying 1 into 1, and then it is keep on popping the elements also. Then 2 into factorial of 1 is calculated by 2 into 1, factorial of 1 is evaluated as 1. Then factorial of 2 has become 2, which is passed on to the factorial of 3, and then we have final result as 6. So, initially your stack starts going one by one, and you keep on pushing the elements, every recent function call is being pushed onto it. As and when we get terminating condition over there, stack starts unwinding and it starts supplying the values to the elements which are behind it. So, another recursion is a very important application of, you can say, stacks in the computer world. So, coming to the next part, which is the next data structure, which is queue. We have already seen static implementations in the series lectures. Now, I am just going to the dynamic implementation. So, dynamic implementation is obviously, which I have already explained, that it can be extended at runtime in most of the application, and queue is such a data structure which needs, flexibility, in the sense it needs expansion, it needs shrinking depending upon the application many a times. Then extension in the array is obviously time taking and inefficient also, and it is almost impossible to be performed at the runtime because of its lots of reallocation. Or initially, if we declare the array large enough, this will lead to memory. Yes, in order to save the memory, we can say that is circular queue can be implemented, fine, but more wastage will happen in the case of linear implementation, and circular implementation is a bit tricky to handle, I can say. So, again we will implement this queue with the help of linked list. So, in a linked queue, each node as on the lines of a stack will contain two parts, one is data and another one is the link part. Each element of the queue points to its immediate next element in the memory, and as it is a dynamic implementation, please remember these elements are not continuous. So, on the screen you can see the picture of an linked queue. It is having elements which is 9, 1, 7 and 4. So, the 9 is the element which was first inserted, then 1 is inserted, then 7 is inserted and 4 is inserted, and now we are having two pointers as in the normal queue, which is front and rear. So, front point is pointing towards the end from which we keep on dequeuing the elements, and the rear is pointing towards the end from which we will enqueue the element. So, front pointer contain the address of starting element of the queue, but remember queue is a FIFO structure which is first in first out. Rear pointer contains the address of the last element of the queue. If both front and rear are null, it indicates that queue is empty. Now, in order to see the common operations on the queue, dynamic implementation of queue, these are insert operation, which is in terminologies of queue it is known as enqueuing operation. It is having a delete operation which is dequeue, and it is having traversal operation. So, for that we need to allocate the memory for new node. Here I have given the statement, coding statement for malloc expression, which will give the allocate the memory for a particular node which is in the form of a structure, and the link or the pointer is being handled by the variable ptr. Now, in order to insert an element into an empty queue, we will check that front is equals to nil. If front is equals to nil, that means the queue is already empty and the new element will be added as the only element of the queue presently. Next pointer of the front and rear both will point to null in this case, and rear and front will both point to that only element added into the queue. So, we will be we are having an PTR, data of PTR will be the item given by the user or the value given by the user. So, if front equals to null, this PTR this PTR will be pointing towards the only node, and so is your front and rear both. So, front equals to PTR and rear equals to PTR are here to ensure that front and rear both are pointing towards that only element, and next of front as well as next of rear are null because there is no other element in the queue. And if this is not the case, that means if front is not equals to null, that means already there are some elements existing into the queue. And if we have some elements already existing into the queue, if we want to enqueue some more elements, we will be inserting or we will be enqueuing from the rear side. So, what are we going to do? The new pointer value will be given to the next of the rear. So, that means now the next pointer of the last node, which is rear, will not be pointing towards the null, it is pointing towards the next new node inserted, and then by the statement rear equals to PTR, we have ensured that we have shifted our rear pointer to the last element or to the newly inserted element, and we have set the next pointer of that rear or next pointer of that PTR equals to null because we do not have any element behind it. In this way, by tackling these two conditions, whether the elements are present already in it or whether the elements are not present already in it, we can handle the insertion or creation of the queue. Coming to the deletion. So, deletion obviously requires checking the underflow condition. If front equals to null, then it is going to be a condition of overflow in queues also. So, deletion operation actually removes the element that is first inserted among all the queue operations. That means we will be dequeuing from the front. So, delete the element that is pointed by the front pointer. If front equals to nil, then obviously it is an underflow condition. Else, what are we going to do? We will be saving that front into the pointer variable, pointing this front to the next variable or the next node available by front equals to front next, and then we will be freeing the pointer as we have done in the case of stacks, if you remember. So, pointer is being assigned to the top, here pointer is being assigned to the front. We have shifted the front and then we have freed the pointer variable available. Coming to the third most common operation on the queues, that is traversal. For traversal also we need to check whether front equals to null. This will help in tackling the situation if the queue is already empty. So, we have, as I have already told you, there is no need or this is highly undesirable to disturb the already set elements, already set conventional pointers like top in the stack or front and rear in the queue. If we want to traverse, we can create some temporary pointers. Here we have created a temporary pointer PTR and it has been given value of front, and if front is not equals to null, that means queue is not empty. Front equals to null, then we will print empty queue and then we will come out of the routine. Else we are on to printing the values. While pointer not equals to null, we will print the data of the pointer and shift the pointer to the next element by the statement pointer is equals to pointer next. So, just print the data and shift the pointer while pointer not equals to null. Start from front and go till rear. So, now let me summarize the whole lecture. We have seen stacks, with their dynamic implementation, all its common operations like push, pop and traversal we have taken into account for, and then various predominant applications of stacks we have seen in very detail, and then finally we have seen dynamic implementation of queues and its common operations. Thank you.